So let's jump into external flow. We'll talk about drag, drag force, lift, lift force, drag coefficient, lift coefficient, skin friction, pressure drag, separation. There's a lot of topics. I guess instead of listing them all, we'll just jump into it. And I'll just ask a lot of questions, okay? So this question, flow fields over most bodies are complicated and can't be solved analytically. Hence, designs often are based on correlations, which are the correlations come from or based on experimental data. It's true. And that's why this chapter, unfortunately, is a lot of plug and chug. It's like, I just kind of get the right correlation for the right geometry, go find the drag coefficient, unravel it to get the drag force. But there's really a lot of application in this chapter. So let's dominate the chapter. Let's really learn the material. Compressible effects. A lot of times we have airflow. Hey, isn't air compressible? When would you need to include compressible effects? Well, compressible effects are negligible with minimal error, meaning, yeah, you're going to neglect something and maybe it'll have a 0.1% error by neglecting it, but it's negligible error. When the Mach number is 0, the Mach number is greater than 0.3, less than 0.3, greater than 10, or less than 0.1. Where's the breaking point that most engineers would say? What's the Mach number again? The velocity divided by the speed of sound, and we're often doing this in air. So you can have a Mach number of a fluid like a liquid, but let's talk about air. Speed of sound in that air. The actual physical speed comparatively. So what do you think? When it's less than about 0.3, which actually is surprisingly high. About 0.3 is the common agreed upon breaking point. So you can have, so do I have to worry about compressible flow when I'm driving 90 miles an hour around my car? Yeah, airflow is 90 miles an hour and I'm driving. No. No. Okay? How about 100? Don't drive 100. All right? But no. Okay? Got to be up to 0.3. How about the drag force? What is this? So we have an object. Let me try and draw an object, like here's a rectangle or box, and maybe it's a long cylinder and it's in cross flow. Or you could have something a little more streamlined, looks like a foil or a wing or something streamlined. That's a bad looking streamlined object. Let me try again. Like that, okay? And you have flow this way. And it'll have a net force, a drag force. It's aligned with the direction of the flow. It's in the same direction of the flow. That's the drag force. So it'll be in that direction. What contributes to the drag force? Two things: skin, what they call friction, and pressure, or form drag, sometimes called form, F-O-R-M, but I think pressure drag, meaning that on this cylinder you have the front side, maybe it's high pressure, and on the back side, low pressure. That pressure imbalance on the two sides gives you a contribution to the drag force due to the pressure, right? The other one is the fluid is fast on the top, fast on the bottom. It's no flow on the side, but that exhibits a shear stress, a viscous shear stress, and so that contributes to the drag due to the viscosity. That's due to the skin friction sliding over it, right? And both of those contribute to the net drag force. When you have a slender object that's streamlined like this foil, it's a bad looking foil, I know, but what will happen is when the flow comes over it, you get a lot of area where the flow is sliding along, and there's not a lot of area where it's negative pressure and the tip high pressure. So for a streamlined object, the drag force is dominated by the skin friction. And for a blunt object, like a cylinder, it's not streamlined at all. It's dominated by the pressure drag. So that may seem obvious, but often engineering is obvious once you understand it. So what is the difference? A lot of it due to separation or the lack of separation. When you have separation, what's happening is the flow stream isn't staying in contact with the body. And so if you're coming over this cylinder like this, you're going to have a hard time because the fluid's coming here and it's going to want to turn up. This fluid's want to turn down. This fluid's turning. This fluid way out here just wants to keep going, right? But this is now going to want to push off, and then you're going to want to be turning it. It's going to separate right there. Maybe it'll reattach later, but it'll separate. That'll be a point of separation right in here. And then coming around here, it's going to want to it's going to want to try and fill in here, but it'll be a big separation region in there. Okay, and it depends how fast the flow is coming. If it's slow, it's able to help negotiate changes in the shape. If it's fast, you get more separation. Here, it would mean if I had a foil, the foil would have, let me try and draw a little better, like that. It would have, for even moderate high velocity coming at it, it wouldn't have any separation. Unless maybe I tried to tilt it. I'm going to try and draw the same foil tilted. See how I changed the angle? If I tilt it, then you can get a significant region where it's separating. And so it separates in this region, creates a big wake region. Okay? So streamlining is to help the fluid flow stay in contact with the surface. What about our drag coefficient? Well, our drag coefficient, we learned from our non-dimensionalization, talking about Buckingham Pi theorem or algorithm, determined relationships. Often you have the relationship that the drag coefficient is a function of the Reynolds number. We did that before, so we're going to use that. We know that's our strategy. Well, what is our drag coefficient? It's the drag force divided by some appropriate area, normalized, so that's a force per unit area, normalized by the dynamic pressure. So often we have our drag coefficient here. We have our Reynolds number, rho, velocity, some length or diameter or some characteristic, some dimension there, divided by mu. And then we'll have that relationship. So the drag coefficient is a function of the Reynolds number. The velocity of the fluid approaching a body is often called. So we'll have the approach velocity coming at an object, and it's usually uniform. And then we'll have an object. I don't know. There's my object, right? This velocity right here is called V infinity. Sometimes you put the symbol subscript infinity far away from the object. Way over here, it's still V infinity. Way back here, it's V infinity. Over here, it's V infinity. But there's a region around the object that's impacted. The velocity is impacted by the presence of that object, okay? But far away, it's the free stream velocity. Give an example of what we would call an axisymmetric flow over a body. So you need to have an axis, and it needs to be symmetric about that axis. So think of an axis, and what type of object would have axisymmetric flow about it? Well, it would be an axisymmetric object. If I took a section like this and then I revolved it, wouldn't it look like, you know, something? If I revolved it, it come down. It's hard to show in 3D, but what would that look like? Like a bullet. Yeah, projectile, a bullet. That would be axisymmetric flow. And then you would be able to solve for it in using the R and maybe Z or Rx, depending on what coordinate you want, Rx or RZ coordinate system. So axisymmetric flow. A lot of our blunt objects aren't. Or blunt or bluff. Give an example of flow over a bluff or a blunt body. What is a blunt or a bluff body? A what? Golf ball? Yeah. Yeah, it's not streamlined at all. It's just a round object. So a sphere or a ball. A football is more streamlined for the flow. And when they throw it, you know, with a particular axis in mind. They don't throw it sideways, do they? But soccer ball, golf ball, baseball, those are not streamlined. They're more bluff. Or let's say I was doing flow over a road and I have a stop sign and I have wind blowing it. Right? Well, the sign itself and the pole would be not streamlined, and the angle orientation of the flow at it's hard to predict. So they just make a pole and they make a sign up there. Okay. All right. Really, the definition of a streamlined body or bluff body is a comparison of the total drag force. It's made up of the viscous component and the pressure drag. Okay, and which one dominates? Which one is most important? Determines basically if it's a streamlined body. If it's viscous, more dominant is streamlined body. If it's a pressure force, pressure drag, it's a bluff body. Lift. So often we have an object in the flow, and it could be a baseball. Let's just consider a simple one, baseball. And maybe that baseball has some rotation. It's flowing, it's moved, the fluid is flowing, and the ball or sphere has some rotation to it. And what that'll do is you'll still have your drag force, right? But you'll also have a lift force. Okay, the way I've shown this rotation of a baseball, can you tell me if the lift force would be up or down? Would the trajectory of that baseball want to curve this way because a lift force is pulling it up, or would it tend to go down because a lift force is down? Without any rotation, there'll be no lift force perpendicular to the direction of flow. But with that rotation as shown, which way would it want to go? Okay, what I'm going to do is take a break. And I'm going to go around and look at your answers. And then I want to also maybe ask a few of you why. All right, so before we finalize whether the baseball goes up or down when it's being thrown, or even a soccer ball. How many people seen soccer balls curve when they kick with a spin, right? And that's all air, isn't it? Now we're just talking about a pool ball on a table, but that's not really in the air that's doing it. It's interaction with the table, the surface, which is a lot of friction, English on the ball. But let's see, baseballs for sure, and soccer balls. What other balls?
The golf.
Golf balls, definitely. So those three balls, they put certain spins to make them go and behave a particular way. I think probably the most dramatic would be soccer. I think soccer, they can really make the ball because it's light.
I think soccer, because you can actually...
So, but before we do the ball, which is a lot harder, let's go back to a nice foil like this. And if I have flow over the foil, and the foil, I have to put a little hump to it, right? Like this. I don't know if I'm doing it right, but it's typically humped a little bit. Did I do a good enough job on the foil? And so when the airflow goes over this wing, okay, is there a net force, a lift force in this direction, or is the lift force in that direction? The air puts a net force perpendicular to the direction of the fluid, okay, and it's either up or down, the net force that the air exerts on the solid object. Up, so that if you had nothing else going on, the wing would tend to go that way, right? It would go, as down the runway, it's starting to go up in the air. True? If its lift is up, right? How does that work? Why? The velocity of the air is faster up here, true? Velocity increase. And the pressure changes. The pressure changes because the velocity is faster on the top of the wing. The pressure is lower. Is that true or not true? What equation can predict that or explain that? Bernoulli, right? Now, we need to stay out of the region so close to the solid that viscous forces are negligible, right? But the pressure can be understood by being a distance off of the solid surface, and that pressure then penetrates into the boundary layer region and is felt, so that the pressure here is like the pressure there. The pressure here is like the pressure there. The pressure here is like the pressure there. Not saying the pressure isn't changing as I'm moving down the axis of the foil. It's just that in and out of that small boundary layer region where the viscous effects are important, right adjacent to the solid, the pressure is felt directly in there. Okay? So we apply a line. We call it some sort of streamline. And it goes like that, and then another streamline, it goes like that. So what happens to the speed of the flow below? What about the speed down here? Is it increased or decreased? Decreased. It decreased. True? The speed goes down? Yes or no? Yes. Decrease the speed. What happens to the pressure? It increases a little bit. Okay? But the real lift is not due to pushing the wing up because of higher pressure underneath. It's really due to a sucking, if you like that term, because of the lower pressure on the top. Both contribute, but the dominant one is the lift, the lower pressure on the top. Okay? All right. So you could do a pretty good job of one just like this. Okay? Flat on the bottom and then shaped on the top like that, okay? And that would make it a negative, 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 negative pressure, and you would get lift, okay? So faster flow by Bernoulli's indicates lower pressure. True? Does that help? Now I give you a minute to think about flow approaching a sphere or a ball that's spinning this way, and you try to predict now or reaffirm your other prediction if you still want to agree with what you had, that the net perpendicular force, I'm calling it lift, will either be in the to make it go up or down. Okay? And that's what I want you to determine. Okay? Did I give you enough hint, enough of a review to help? So now you have it down. Okay, who else can, that's right. I think people agree that because of the spin, it'll feel the force down, right? Which would make it want to curve the ball, soccer ball, tennis balls have spin too, don't they? Tennis balls would curve like this, okay? So now, why? What helped?
The spinning.
The spinning, yeah. The way I do it is I think of the poor little chap that's going to hit spot right on the middle of that ball. He's heading straight for it right there, right? And that little fluid packet that's going straight for it has a 50-50 chance to slide to the top or to the bottom. But now that I have spin, which way is that little chap going to go? He's going to go to the bottom. Not only is he going to go to the bottom, but maybe the one a little bit above him will also be grabbed and swept to the bottom too, true? So it's like more than 50% of the flow is going to go to the bottom. which means it has to go faster to get around the bottom. When it goes faster to get around the bottom, pressure goes even lower from Bernoulli. Does that make sense? And now it was pointed out it's example 11.6 in the textbook, right? So I read example 11.6 for the spin. All right. But basically the lift coefficient's always perpendicular to the direction of the flow. The blank force, the drag, the lift, the draft, the vertical or the wake force is the force a flowing fluid exerts on a body in the flow direction. Which force is that? C. And the blank force is the force a flowing fluid exerts on a body perpendicular to the flow direction. Lift. Okay? And I know it's always a little disconcerting because what they'll do is they'll put this nice aerodynamic aircraft wing, right? And then they'll talk about from this point to that point, and then you have an orientation of it, okay? And then they'll put that orientation in direction of a flowing fluid, and then they'll talk about some angle of attack, right? And if the angle of attack isn't much, you get a lot of lift. And maybe what happens is you change the angle of attack, maybe it helps a little bit with lift, but if you change the angle of attack too much, what happens? You create a big wake region. It separates, it doesn't flow. It's like, how about if you take that nice foil and try and flow it like this through the air? What do you think that's going to happen? It's not streamlined at all in that direction, right? You took the angle of attack, moved it to 90 degrees. So anyway, you never take it to 90 degrees, right? Unless the airplane's shot down and it's just falling. But what happens is the lift force is still in this direction, and the drag force is still in that direction. Yes?
Is there a standard angle that you cannot add?
I'm not an aero guy. There's a couple aero guys in faculty, and they would love to answer that question, even though they don't teach fluids. But it's common to describing too much. And then you have stall. Once you have stall, you lose it. True? So, and I think it depends on your foil, your shape of your wing. Drag is caused by two different effects. I'm going to pause. I want to see your answer to this. Don't call it out. All right, so this one is pressure and friction. The best answer. Terminal velocity. So I take an object, and maybe it's a ball, and I just drop it. I start at 0 speed. I drop it at rest in a fluid. And so then the fluid appears to be going at faster speed as the ball drops, true? And after some time, I might be able to plot the velocity, or maybe I do this, leave the air quiescent and the ball fall. And I talk about the velocity of the ball, and I start it at 0 speed, and as a function of time, it's going to do something not very dramatic, is it? What's it going to do? Taper off. It's going to accelerate rapidly as I drop it, but then after a while, it's going to reach a velocity called the terminal velocity, true? So this speed right here is the terminal velocity.
Is the maximum velocity?
It's the maximum velocity of free fall in that fluid. Okay, so how would I calculate that terminal velocity? Well, I would do sum of the forces equal to the mass times the acceleration of my object. And the mass of the object, dv dt for the acceleration. How the velocity is changing with time. What are the two forces acting on this object? It's in a gravitational field. Otherwise it wouldn't fall. And so it's going to be the weight downward, mg downward, and that's going to be in my positive velocity direction, a positive, x direction. This is all positive x. Minus what's going to be making it resist falling, the drag force, Fd. Right? Fd. Now, during this time, in here, what's happening to the acceleration? What's happening to dv dt? That's not zero. It's non-zero. But what happens out in this region? What's the acceleration of the object? Zero. So what's the change in the speed with time? Zero. So what happens to the right-hand side of the equation? Zero. And so we find that the drag force is equal to the weight, and that gives us the terminal velocity. What's our equation for the drag force? Is it the drag coefficient times the pressure velocity times the area? Whatever appropriate area was used in the definition of the drag coefficient. That's right? True? Makes sense? So here you could now solve for V if you knew what is that drag coefficient. Yeah, if it's a function of Reynolds number, well, then I have to know the speed to get the Reynolds number, and then to get the drag coefficient, so it may be iterative or it may be a constant. If it's a constant, then I can get V terminal if the drag coefficient is equal to a constant, then V terminal is equal to the mass times G divided by the drag coefficient, 1/2 rho area square root. Wouldn't that give me the equation for did I do the algebra correct? Yeah. But again, this drag coefficient could be a function of the Reynolds number, and the Reynolds number is a function of the velocity. Rho Vd over mu. Let's do this. Let's consider slow flow, low Reynolds number flow. They give it a particular name. It's called Stokes flow. If you see that word like Stokes flow, it's like, ooh, this is a very low speed flow. Okay? There's a lot of applications of very low speed flow. Things moving in liquids very slowly, things moving in air very slowly. Typically, maybe it's just settling. Maybe I have something and I have some solids and mix it with the liquid, and then I shake it all up, right? Then I let it sit on the table for a while. Maybe it takes a couple hours, maybe it takes a couple days, but it all settles out. Very slow settling. That would be like Stokes flow. Well, for low Reynolds number flow, the drag coefficient, a constant divided by the Reynolds number. It's just like in another application. What application did we have the friction coefficient, the fanning friction factor, F? Laminar. The friction factor is 64 over Reynolds number. It's laminar flow in pipes, right? But here we have very low flow. Let's think about our sphere or ball, and our fluid comes in here, okay? If it's very low flow, it'll just slowly creep around and come back around and join back together, just like that. Okay? And so the pressure here and the pressure here will be exactly the same. And the only contribution to the drag force will be nothing from the pressure, but everything from viscous drag. Because it's moving around, it's got a shear stress, shear stress, shear stress, shear stress, shear stress, shear stress. Always trying to hold it back. All right? So you get this constant over Reynolds number. What happens if I had really low flow over a different object other than a sphere, maybe a long cylinder? Well, it changes the value of the constant. But the general form is C sub D is equal to constant over the Reynolds number. True? The drag coefficient is defined in terms of the frontal area for bluff bodies. True or false? What is that area in the drag coefficient? Yeah. So if I had a sphere and I looked at it, I know it's kind of funny because a sphere has a projected area that looks like a circle. What would be the area of a circle for this projected area or frontal area of a sphere? Pi d squared over 4. True? Now, sometimes somebody say, hold it, the area of a sphere. I have a sphere, I'm thinking about it. What's the surface area of a sphere? Isn't the surface area of the sphere 4 pi r squared, which is pi d squared? Hey, these are not consistent. They're not equal. So either the area of the sphere is pi d squared, or the area of the sphere is pi d squared over 4. Which is it? Which area do we use in the drag coefficient? It's the frontal area, the projected area. Okay? So if I put a sphere on the road and I stay way far down the road, a mile away, and I look, that's the shaded area, the frontal area. Just think of also automobiles. That's the frontal area of the automobile. Okay. The drag coefficient is defined in terms of a planned form area, not the frontal area, for slim bodies such as airfoils. What? So if I take my airfoil like this, right, it's a slim, okay, they say the drag coefficient's defined in terms of the planned form area. What's the planned form area? Well, it's looking down area. It's this length times the depth into the board. What do you think? You agree? So be careful when you have drag coefficients, because the area for a blunt body or a bluff body is different than the typical area for a streamlined airfoil body. Okay? And why? Why did they do that? Because in this body, what dominates the drag force? The two competing things, what dominates? The viscous, the viscous, the viscous. And then for this object right here, the bluff body, the blunt body, it's not viscous drag that dominates, it's the pressure drag. It's the, what they call, some of them call it form drag, but form is not very formative. But form meaning it's due to the area because of a pressure difference on the side. The chord of a wing is the line connecting the nose and the trailing edge, or the length of the top surface. So I would, actually do the length if it bowed up, get the length there. No. It's from the nose to the trailing edge. That's the chord. Okay? That's a straight line length. That's the chord of a wing. True? Which statement is true? Right, I'm going to pause and let you chew on it for a minute and then come on with your answer. So we back up, we'll answer this question. Calculate the drag force when it's only due to friction drag from first principles. What does that mean? Somehow, if I had this shape of the object, okay, I would be able to come in here and get tau. What's tau? Right there at that surface. And get tau right there and get tau right there. What do you mean by tau? What's he mean? What is tau? It's the shear stress. The shear stress acting at the surface, right? Viscous shear stress. Isn't tau given by somebody's law of viscosity, mu du dy at the surface. All right? So if I knew how the velocity, how steep it is, the velocity profile at the surface, and then I knew the fluid viscosity, right? Make the multiply, I would get tau. I would get the shear stress. That's a force per unit area, right? And then I would do this. I would say tau dotted with, I'm going to say dA, but this, I need to do something here. I need to do like a N dA. I need to think of it as a stress, so it has a direction to it, and then I have an area vector because I want to pick off, or do it this way. Do tau in the x direction only. So this, at this location, it may have some y component and x component. I just need the x component of it, right? The shear stress. I'm just getting the x component, the x component, the x component over the area. Sum them all up. Wouldn't that be like friction drag over all the area? In the x, it's in the x, right? In the x direction. Does that help? So when I'm calculating the drag due to friction, if I change the viscosity, I'm changing the shear stress at the surface. It's a strong effect. So right away, we're going to throw out weak, no, and no. So now we're down to two answers, either A or C. And increases with increasing viscosity. Yep, so it's A. I think that statement's reworded straight out of the textbook, okay? Right. So now that we've beat up on low Reynolds number flow, what did we find? We found that the drag coefficient's inversely proportional to the Reynolds number. How do we calculate the actual drag force? We unravel it. So we'd have the actual drag force is equal to the drag coefficient times the velocity pressure times some area. Okay, let's do this. If it's a constant over Reynolds number, rho v, let's work with the length is a d. D or L, which one do you want? D for diameter, L for length. Let's work it with D, mu. All right, times 1/2 rho v squared times, now for our projected area on a sphere or something diameter d, pi d squared over 4. The length scale I'm not that interested in, nor the value of the constants, but what does this show? It shows that, is this v right here the same as this v?
Yes.
It is, and so we can cancel one of those. Okay, so we get that it's a constant times a viscosity. Is this rho and that rho the same? We can cancel. This length scale and that length scale, one of those length scales the same? True, true. So I know that I have a mu and a v. Whoops, I didn't want to change color, just a v right there. And then I had some other constants, so I have pi over 8, right? With a d, with a d, with a d. Okay, so maybe I do this is I move the pi over 8 over here, because that's just a different constant, and move the d over here. So you see that the drag force for low Reynolds number flow, for Stokes flow over something like a sphere, is proportional to the fluid viscosity, the speed. Often we think of terminal speed as it's settling out of the object if it's only settling under gravity, and also some length scale like d diameter. So f of d is proportional to v. It's proportional to that speed. Okay. When you get to the intermediate Reynolds number, before you get to high, it's typically low and then high, but in between intermediate, this c sub d is truly a function of Reynolds number. But when you get to high, guess what? It's now a constant again. But it's not constant over Reynolds number, it's just a constant. And we've seen that before, where you'll have the drag coefficient come down, maybe do this, and then it goes flat as a function of Reynolds number. High Reynolds number, the drag coefficient's a constant, especially for bluff bodies, okay, where you have flow separation and it's turbulent flow. Okay, we can do this. Let's work out what the drag force is. Excuse me. Let's work out what the drag force is for high Reynolds number flow when the drag coefficient's a constant. Do the same type of thing. We say we unravel f of d is equal to c sub d times 1/2 rho v squared a. Right? And this time we can't unravel this c sub d. It's just a constant. So we find that c sub d may be, what was this area? Pi d squared over 4. So 4, we had the 2 from the half, we have the rho, we have the v squared, and we have the d squared. Is that right? Did I do it right? So these are just the constants. And we have now rho, velocity squared, and some size of it, diameter squared. So what you find is that it's a stronger function of the speed. The drag force, if I wanted to just plot the drag force as a function of speed, at low speed, low Reynolds number, it would just be linear. At high speed, after some transition, it would be quadratic. I'm trying to draw where it's proportional to v squared, it's proportional to v. Make sense? So if you are in this region and you double the speed, double it, you doubled the drag force. But if you're out in this region, you could double the drag force just by maybe increasing it a little bit, you know, by a factor 1.2 or something, you know. If I wanted to double it, all I would do is take, the new speed would be the square root of 2 times v, or 1.41 times v, right? I don't have to double it. Just a 40%, 41% increase somewhere in there. True? That I have doubled the speed. All right. I mean, doubled the drag force. At high Reynolds number flow over common geometries, the drag force is a constant. Do you agree? High Reynolds number flow.
Constant, true.
True. For high Reynolds number flow over common geometries, the drag coefficient is what? Is the drag coefficient proportional to the Reynolds number? Is the drag coefficient inversely proportional to 1 over Reynolds number? Something like that, this constant proportionality, etc. Which one is it? It's what letter?
C.
C is a constant and does not depend on the Reynolds number. Now, if you look at answer D, you know, is a constant that depends on the Reynolds number. It's like, is a lightweight heavy object. What? Is a, I don't know, is is a well-lit night, dark night with no moon. What? It just doesn't make any sense. D makes no sense, does it? It doesn't make any sense. So, all right, how about the next question? For high Reynolds number flow over common geometries, the drag force, this F of D, not to be confused with the drag coefficient, which is C sub D. The drag force is which answer? I'll let everybody think of it, and then I'm going to check their answers, okay? So there you go. Just remember, these, when they say common geometries, it's not streamlined. So it's going to have a high Reynolds number. It'll taper off to a constant drag coefficient as a function of Reynolds number. And then when you unravel it, you find that the drag force is proportional to the speed squared. That's a very important observation in fluid mechanics. Because a lot of times we talk about vehicles. So as a threshold, I know a lot of people are still, they're in kilometers per hour, right? But miles per hour, about 25, 30 miles per hour, the aerodynamic drag force on your vehicle is negligible. If you're driving that speed, right, it really doesn't take much power to overcome the air. But if you start going 50, 60, 80 miles an hour, you have a appreciable amount of power devoted to overcoming the aerodynamic drag. All right? So the drag coefficient on vehicles is very important, and you'll see the drag coefficient quoted for a large number of vehicles. I think I've taken you to the website. I'm going to take you there to another Wikipedia website and show you drag coefficient. Oh yeah, bicycle as well, any moving vehicle. Now, first of all, the bicycle is a different character because you don't have an engine that's 50 horsepower putting power into it. And so you're going a lot slower. And the body can't put a lot of power in the pedaling continuously. So I don't know what braking speed it is where below, but I would probably say maybe 10, 15 miles an hour. Yeah. Anybody a biker? They're all over on the streets around my place on the weekends. No? That's what we're talking about. So how fast do you need to go before you're like, no, this aerodynamic drag is killing me. I'm going to slow down, right? You don't go that fast? Okay, well. All right, so the drag coefficient for vehicles are quoted as single numbers. Let's go take a look. So if you just go drag coefficient, first of all, this is a good website. You can get a lot of information off of Wikipedia. So here they give you the drag coefficient for a sphere, 0.47. For half a sphere, 0.42. For a cone, 0.5. You can check these with another source, but they're probably pretty good. Streamlined body, look at the drag coefficient. It drops a lot. You start getting down to 0.1, even 0.15 or 0.2. That's pretty low drag coefficient. And but you're only going to get that for streamlined bodies. Here's our classic formula. C sub D is F of D, 1/2 rho V squared A. A is a reference area. Okay, it's not always the frontal area. It depends. And notice they did the same thing. For a sphere, it's pi r squared. Note, this is not the surface area, 4 pi r squared. Right? I wonder if I give an exam question, some student will say, oh, the area of a sphere, 4 pi r squared. When they need to use in this equation the area. Also, for airfoils, the reference area is the planned form area. Okay, there's some more discussion. Talk about pressure distribution as it's coming at this plate, on the plate. See? So the flow around the plate showing the stagnation. That would have the highest pressure, wouldn't it? And then the lowest pressure as you're kicking around. Whoops. Let me scoot down. We're going to spend some more time on the spheres, but this is a drag coefficient as a function of Reynolds number. Let me just click it. Can you see that they put this where this looks pretty straight line-ish at low Reynolds number? So that's in the low Reynolds number region, the drag coefficient divided by the Reynolds number. Constant. The drag coefficient is equal to constant over Reynolds number, right? But then what happens is you still have laminar flow over it, but you start getting, it's difficult to recover the pressure to come around the backside. Something happens on the backside. It starts shedding vortices, the little street of vortices being shed. As you increase the speed, it even becomes more difficult. And you develop separation points in wakes region. And then what out here, you start to get the very high Reynolds number. What happens is you dip down and then back up. You had laminar flow on the front half coming around that sphere. All right? But if you go faster and faster, you get turbulent flow earlier on the front half of the sphere. The turbulent flow is able to negotiate the bending around on the back side of the sphere better than laminar flow. And the size of the wake on the back side when it's turbulent gets smaller. Slightly smaller such that the drag coefficient drops. And then, because it's still increasing, it'll kick back up and go back up. But this is interesting behavior. And so when they make golf balls, they thought, this is great, but I really don't want to have to hit it that hard and go that fast as Tiger Woods does. I'd like it to be turbulent earlier at lower speeds than a smooth ball on the front half. So what do? They put a little roughening on the golf ball. What's the roughening they put on it? The little dimples, right. And so with those dimples, it actually helps promote tripping to turbulence earlier. So at a lower Reynolds number, the red line comes down, dropping the drag coefficient, dropping the drag force, dropping the drag resistance, hence your ball is able to go further with the dimpling. How many people heard that? One? You're a golf player. Anybody else? Yeah, that's a good phenomenon, isn't it? So there you go. Let me jump back. Here there's a great description, attached flow. So it's Stokes flow. Hey, we just learned that word, didn't we? Stokes flow. Yeah, slow. And you still have laminar flow, but now you have some vortex street. Oh, let's go take a look at the vortex street. So they're showing you how it's dynamic, it's shedding kind of the vortices. They're regions of rotating fluid. Okay? On this, and they come off at a certain frequency, but this is only under like laminar flow conditions with a range of Reynolds number, which is narrow. Let's go back now. All right. And then as it goes up, you have separated unsteady flow, and then post-critical turbulent boundary layer 5 right in here. Turbulence. That's going to go back up. So smooth sphere at 10 to the 6 Reynolds number, 0.1. Smooth sphere at 10 to the 5, 0.47. You can see some values quoted. Here's some vehicles with low 0.25 is a very low drag coefficient. True? How about a bullet? 0.295. Rough sphere at 10 to the 6 is 0.48. And then let's see if Empire State Building, well, it's high, yeah. You have to consider wind loads on buildings as a civil engineer. And road, bicycle in the touring position, 1.0. So you can get a lot of drag coefficients. Aircraft have very streamlined bodies, a lot lower drag coefficient. And it's the frontal area for automobiles and many other objects. But for aircraft, use the wing area as a reference area when computing C sub D, that planned form area. Different area, okay, for the airfoils. And they talk about bluff and streamlined bodies. The drag made up of pressure contribution and the friction. Here's how you might want to calculate the pressure or pressure difference integrated over the area. Here's a shear stress, and you're getting that component in the x direction. That's what they're showing you in mathematics, an area integration. Aerodynamic drag coefficient on automobiles is negligible at low speeds, less than around 30 miles per hour. True. For a car moving on a flat road at a high speed, 60 miles an hour, the power developed by the engine to overcome the aerodynamic drag force is the power. Now this is new. What is the power required by the automobile engine to overcome the drag force? Is it the power? Is it independent of the vehicle speed, like a constant? Is it inversely proportional to the vehicle speed? Is the power proportional to the vehicle speed, so it's equal to some constant times this vehicle speed? The power proportional to or equal to a constant vehicle speed squared, or the power constant vehicle speed cubed, squared or cubed? You see all the choices? Why don't you work on that for a minute? All right, so let's go ahead and give a hint. So the hint is that if I have an object, right, and I exert a force on that object, F, and I move that object a distance x, I did so much work. Let's say the force was always a constant as I moved it over the distance x. The force did work on the object equal to the magnitude of the force, the length of distance of movement, true? That's the work that the force F did on this object. Somebody says, this force is being applied to an object, but I'm not thinking about moving a distance. I'm thinking about moving at a speed v. But the speed v is dx dt. It's the rate at which it's moving. True? So now I don't have a work, I have a rate at which work is having to be done on the object, or the power, right? Power, energy per unit time, work per unit time. And what's that equal to? You got to know this. You have to own this equation. This is just a review of mechanics, nothing to do with fluids. This is just a review of dynamics. I know that some of you already have it, but some of you didn't. Those that didn't already get the answer need to share with me. So the work is F times X, the power, the rate at which work is being done with time, constant force F. Does this equation make sense? Isn't that what you needed to use? For those that got it correct? I'm going to walk around and make sure 100% get this correct, because it's just too important. So what we find is the answer is E, true? So you have the force is proportional to the speed squared at high Reynolds number. And then you have V times V squared it's proportional to V cubed, constant speed cubed. So this was my question. Let's say I am driving 60 miles per hour, and that's my initial speed. And then I boost the speed. I want to gun it now. I'm really ripping down the road, and I want to go 70 miles per hour, right? How much more horsepower is my engine going to have to put into the drivetrain to accomplish that, just to overcome not the additional frictional effects in the transmission and everything else, just aerodynamic drag, right? Because that power is being dissipated to push the air out of the way. It's aerodynamic drag, right? So the aerodynamic drag, the power W dot case 1 divided by velocity 1 cubed is equal to the power for the second case, the velocity of the second case cubed. So the new power is equal to the original power times the new speed divided by the original speed cubed. Let's say I wanted to go from 60 to 70, 60 miles an hour to 70 miles an hour, 7 over 6 cubit, right? What's 7 over 6 cubed? 1.58. Is that what you had back there? A 58% increase. To improve the fuel economy for a low drag automobile, it is better to turn the air conditioner off and drive with the windows down or open. False. Okay? Just leave it sealed up because, as somebody said, it's like a parachute. When you open those windows, the wind is whipping in and you significantly increase the drag. And they spent a lot of time and energy working on that car to reduce the drag coefficient. And they're going to do it with the windows up in their testing. Okay. Yeah, keep your arms in the in the thing. You ever drove down the road and, I'm sure that when you're young you did it, you're experimenting, you feel your hand out the window, and then you go a little faster, put your hand out the window, and you feel the drag? True? Yeah. And when you get a lot faster, it is severe. I don't know. I can't remember doing that over about 60 or 70 miles an hour, but you don't probably want to stick your hand out the window going any faster. All right. To calculate the drag force on a complex body, treat the body as a composite of two or more simple bodies, calculate the drag force for each of the components, and then sum to estimate the total drag force. This is known as the, something principle. The superposition principle, the supposition principle, the dereliction principle, the determination principle, or the hydrophonic principle. I wait and I walk around to see your answer. So this would be that stop sign with a pole in the wind. You would first do it for the stop sign, calculate the drag force, then the pole, calculate the drag force. And if you needed to worry about the moment around the base, well, then you could consider the distance or the location for the moment calculation. But otherwise, just get the drag force, right, on a complex body by doing parts and summing them up. So I pause, but UTSA group. So the superposition principle. Flow over a flat plate. So when you have a flow over a flat plate, first of all, the flow, you just worry about one side of it. Have a very thin plate and one side of it only. And so the flow is coming at it, and you develop, because of the no-slip boundary condition, the flow adjacent to the top surface is zero velocity. So you have a singularity right at the tip. It's like right before the tip, it's coming at it. Right at the tip, it's no speed. But you have a region where the flow has been impacted by the solid, non-moving flat plate. Out in this region, the fluid is everywhere at V infinity. Over here, V infinity. Over here, V infinity, right? So if I wanted to plot as a function of y, the velocity profile starting at 0, it would be 0 here, and it would go out, it'd be like that. And so this distance from here to there, that distance is delta. It's called the boundary layer thickness. The boundary layer thickness. It's the region of the zone of the fluid that's felt the impact of the stationary flat plate. And so its speed is less. And so the speed goes from 0 up toward V infinity. Well, that thickness is defined by knowing or estimating the velocity as a function of y. And so the velocity, u, at y equal to delta, that's out that far, is defined to be 99% of V infinity. It's not 100%, it's 99%. Professor, why didn't somebody say 95%? They beat you to it. The textbooks all have 99. But couldn't it have just as arbitrarily as said it was 98%? You're absolutely right. And it would be a different boundary layer thickness. But guess what? It's all 99%, okay? So there you go. That helps define the thickness of the boundary layer. Now, this friction coefficient, C sub F, is related to the force or the stress per unit area, the viscous shear stress at the surface. And it's normalized by the dynamic pressure. So these are both forces per unit area. True? Okay. How do I calculate the viscous shear stress at the surface? Mu du dy at y equal to 0. True? Whose law? Newton's of viscosity. Now, as I continue to go down a very long plate, what happens is some places and some plates, they'll start to do a transition, and then they'll go turbulent. I can't spell turbulent. Let's spell turbulent. Turbulent, okay? Meaning, in this region, the flow is not laminar. It's going in different directions, mixing, okay? Here, it was all laminar flow, all in here. But then something happened where the laminar dropped down, and you still have a layer. It's a viscous sublayer of the fluid, which is laminar in nature, but the majority of the boundary layer is turbulent. And the growth of the boundary layer has increased when it became turbulent. All right? What is this region? It's really not laminar anymore, and it's not turbulent. Would you like to give it a name? Transition. Transition. All right? So what they did was they say, we can introduce a Reynolds number, RE, which is just like everything else, rho V infinity over mu, but I don't know what length scale to use. So we'll introduce the Reynolds number based on a length scale where x is the distance from the leading edge. And so close to the leading edge, it's small. But as I move x further away, x grows and gets larger, larger, larger. The Reynolds number gets larger, larger, larger until you get around a critical Reynolds number, which for flow over a flat plate, you would have never guessed, is 500,000. It's your annual income, annual salary after a few years being employed as an engineer. 500,000, wouldn't you say? Let's vote. Is that what you like? Annual income, 500,000? All right. No, there's no way to have guessed this a priori. They experimentally measured it, and they found out it's not precise. It's in the vicinity. Maybe it starts at 100,000. Maybe it goes a little bit larger, but the critical is agreed to be 500,000. 5.5 times 10 to the 6. 500,000. Hopefully you can remember that number. So that's where it transitions. I think we're going to be close to being out of time. For flow over a smooth flat plate, the transition from laminar to turbulent occurs when the Reynolds number is about. You have very good short-term memory recall. What is the friction coefficient C sub F defined as? Shear stress at the surface divided by 1/2 rho V squared V infinity. Now, would this be a function of x? It would be a function of x because it's a local. You'll have both a local shear stress and a local friction coefficient as well as an average. The average. Well, the average is not that hard. C sub F averaged from 0 to L is equal to 1 over L times the integral from 0 to L c sub f of x dx. It's just averaging. You just do the average. Sometimes they put a bar over it, say this is the average. Okay? That's used sometimes in textbooks to indicate the average friction coefficient. Define the Reynolds number for flow over a flat plate, RE. Rho V X, yeah, V infinity or just V. Some people leave off the V infinity over mu, but this is the free stream velocity. Okay, what is RE at L? Rho V L over mu, where this plate stops somewhere, and that distance, the length of the entire plate is L. See? So one of them is called the leading edge. One of them is called the trailing edge. This is the leading edge. This is the trailing edge. And so you can get the Reynolds number would be the Reynolds number. REL is the Reynolds number at the trailing edge. And that would be your maximum because it's the largest length, the longest length, XL. Okay? So a lot of times they'll say, well, let me do this. You have flow over a flat plate. Let me just check the Reynolds number at the trailing edge. Is it above or less than 500,000? If it's less than 500,000, the flow is always laminar over the whole thing. If it's above 500,000, then I know the transition happened. Did it happen in the middle or near the end, near the beginning? It all depends. You got to find out where that critical Reynolds number, that critical, oh, it happened right here. Well, then most of the flow is turbulent. What happened right here? Well, most of the flow is laminar, and then a little bit turbulent at the end. What is the difference for flow when it approaches a thin, knife-edged flat plate versus a thick, box-edged flat plate? Here's the flow field, A and B. They're approaching something that looks like this, knife-edged flat plate, flat on the top, but it has to have a knife cut on the bottom, versus this. This one, you're going to be able to get a nice developing flow. Talk about the fluid flow, the velocity of the fluid right at that corner, not at the solid surface, just a little away from the solid surface. What's it look like? It's going to be trying to go this way as well as that way. Why? Because half of the fluid here wants to get around, and half of the fluid here wants to get around. And so it's not going to be coming in only in the X direction. It's going to be coming strongly in the Y. And what will happen is, somebody already said, I can envision a nice separation region right in this region, right? Before it gets back to being flow down the length. But if you have a knife, thin, knife edge, flat plate, it's just down as you go. Okay? So you'll see that terminology, and that's what they're trying to avoid, is the separation at the tip right there. What is the criteria for the boundary layer thickness? How do I calculate the boundary layer thickness? Somebody says, I want you to tell me what the boundary layer thickness is at this location, you know, down the plate, the thin edge plate. At this location X, tell me what delta is. How do I calculate it? What's the criteria? Short-term memory recall. I just had the equation up. What was the equation? 0.99 something. So you have to think about U as a function of Y. And it starts when U is at Y equal to 0, it's 0, no slip. U at Y equal to infinity, far away from the plate, V infinity. It's U, I can't write U. U at Y equal to the boundary layer thickness is when it's 99% of V infinity. That's how you define. This is a funny way of writing the definition for finding the boundary layer thickness, but that's the way you do it. Flow inside the boundary layer is rotational. Well, what's rotational mean? It's meaning it's wanting to turn. If I put a happy face in here, right? And I can't draw a happy face, but here's my happy face. Would the happy face later on be rotated and then have it like this? Yeah, it would, because the fluid, as it's going further out, is faster. The fluid closer in is slower. And so it's rotational flow. How about the fluid flow outside the boundary layer? Is it rotational? Go out here, put a happy face in. Is it still like this? The flow outside the boundary layer is rotational? No. It's irrotational. Inside, rotational. Okay. We're good. We're done. Thank you for your attention.